Hello, and welcome to Symbolic Logic, Unit 6, Introduction to Truth Tables. So far in this class, we've looked at developing formal methods for assessing whether or not arguments are valid. In our first week, we talked about the concept of validity and transformed some arguments into premise, conclusion, form. Last week, we started learning about sentence letters and the connectives, and this started allowing us to think about making formal representations of arguments. That is, representations that capture the form of an argument while abstracting away from the particular meaning of sentences that go into it. Today, we're going to continue our investigation of the validity of arguments. And we're going to do that by learning about what are called truth tables. So we'll be introducing the truth table method, which is a way of assessing a purely mechanical procedure for assessing various logical properties. Some of those logical properties we looked at earlier, such as necessity, contingency, or inconsistency for a single sentence, equivalency, consistency, or inconsistency for a pair of sentences, and then ultimately the validity of arguments. So we'll be learning about truth tables and seeing how later this week, how these methods allow us to investigate the logical properties of different sentences or sets of sentences. Okay, so again, just to remind us, we have our truth functional connectives, which we discussed last week. The logical connectives that we're studying, and again, these include negation, disjunction, conjunction, the conditional, and the biconditional, and that's all of our logical connectives. There are 5 of them. These, of course, allow us to make more complex sentences from atomic sentences, but they also have another important feature. They're all what logicians describe as truth functional. So this means that in order to know the truth value of a sentence formed using atomic sentences and the logical connectives, all we need to know is the truth value of the atomic sentences. We don't have to know what the atomic sentences actually mean in order to know if a complex sentence used with them is true or false. We just have to know what their truth value is, not what they actually mean, and then know how our connectives function. So for example, consider the sentence A and B. If we know A is true and B is true, then we know A and B is true without knowing what A means or what B means. A could mean anything. It could mean cats are furry. It could mean pizza's delicious. It could mean the sun or the Earth's orbits the sun. Same with B. B could mean anything. As long as it's true, then we know, as long as A and B are true, then we know that A conjunction B will be true. And this is true for all of our truth functional connectives. So we can say the same thing about other of our truth functional connectives. So again, we can know the truth value of a complex sentences that uses only logical connectives so long as we know the truth value of the atomic sentences that compose it. But there are other things that function sort of like connectives in natural language that don't have this feature, right? That are not truth functional. So for example, compare conjunction to the non-truth functional connective and then. Okay, so suppose A is true and B is true. Then A conjunction B is true. But this doesn't hold for the connective and then. So consider 2 sentences. So A, this is true. The dinosaurs went extinct. That's what sentence A stands for. The atomic sentence, the dinosaurs went extinct. And we'll take B to stand for the Earth's crust cooled. Now, these 2 sentences are true. And if we combine them using conjunction, we also get a true sentence. So A and B will be true. However, we can't make that same assumption for A and then B, right? So and then doesn't have this feature. So A and then B is false, right? Because the Earth's crust cooled before the dinosaurs went extinct. So and then is not a truth functional connective. We can't determine what the truth value is of a sentence used with the connective and then merely by knowing the truth value of the atomic sentences that make it up. We need to know something else. We need to know how those sentences relate to each other in the temporal sense, which one came first. So truth functional connectives are very important. they have this unique feature. Notice also that B and A remains true, right? So just if we have that truth value, I mean, if we know that B and A are true, then B conjunction A remains true. But B and then A also goes true. But clearly its truth value depends upon something other than just the meaning of the sentences themselves, since A and then B was false and B and then A was true. Okay, so many connectives of natural languages like English are not truth functional. So we've talked about and then. There are other connectives that are also not truth functional because that exerts or suggests some relationship between the two atomic sentences that are make up a sentence using because. If you know the dinosaurs went extinct because the Earth's crust cooled, well, that's false. But another sentence, you know, the dinosaurs went extinct because a giant meteor hit Earth, that would be true because the appropriate causal relationship's there. So we'd have to know what the sentences mean and what the causal relationship is, what the atomic sentences mean, and what the causal relationship between them is to assess whether A because B is true. But again, that doesn't hold for and or our other or conjunction or our other logical connectives. Another example, Jimmy Olsen thinks. Jimmy Olsen thinks some true things and some false things. So we can't simply infer from the connective Jimmy Olsen thinks and some sentence, whatever its truth value is, true or false, that the complex sentence is going to be true, right? Jimmy Olsen thinks P. If P is true, then Jimmy Olsen thinks P may be true, but it may also be false. And the same holds if P is false, right? So Jimmy Olsen thinks, although functioning sort of like a connective, is not a truth functional connective either. And there are many more of these non-truth functional natural language connectives that we can point to, but we're not going to spend a lot of time talking about them because we're interested in the logical truth functional connectives that we've already discussed, or that we've already introduced. And again, those are conjunction, disjunction, negation, conditional, and biconditional. All of these connectives are truth functional. So because these are truth functional, we can also actually construct truth tables to determine the logical features of SL sentences. So the truth functionality of our connectives is importantly connected to this new method we're going to be learning, the method of truth tables. So we've seen this a little bit already when we've thought about the characteristic truth tables for connectives. So one example, or I'll try to move that down a little bit and see if that helps. No good, we'll move it back up. So last time, you know, we used truth tables in talking about our connectives. This happened in lecture 5 last week. So when we walked through the connectives, we talked about, we used truth tables to define their properties. So we said the following about the connective negation. So if we have phi, and here with truth tables, we're going to use 1 to stand for true and 0 to stand for false. This is sort of like binary. So 1 means true, 0 means false. Well, if these are the truth values for our underlying sentence phi, right? Or, I mean, these are the possible truth values of it. Suppose the sentence is something like Mark is hungry. That may be true sometimes and false sometimes. If right now it is true that Mark is hungry, then the sentence, it's not the case that Mark is hungry, will be false. And similarly, if it's false right now that Mark is hungry, then the sentence, it's not the case that Mark is hungry, will be true. So this little truth table tells us the values of these connectives, what their value is going to be in instances where the underlying atomic sentence or the underlying sentence that's modified with the connective has different values. If the underlying sentence is true, then negation phi will be false. And if phi is false, then negation phi will be true. So a truth table can be used to define the features of connectives, and we've seen this with other of our connectives too. So for phi and psi, if phi is true and psi is true, then it follows that phi conjunction psi is true. But if phi is true and psi is false, then phi conjunction psi is false. If phi is false and psi is true, then phi conjunction psi is false. And if both phi and psi are false, then phi conjunction psi is false as well. So this records the truth values for complex sentences using conjunction. We can construct a truth table, a simple truth table to record the truth values of disjunction, right? So we know that if phi and psi are both true, then phi or psi will be true. This is because we use a inclusive or. That means a conjunctive sentence is true. I'm sorry, a disjunctive sentence is true so long as at least one of the disjuncts is true, and also if both of them are true. So phi, psi, if they're both true, then phi or psi is true. If phi is true and psi isn't, then phi disjunction psi remains true. And if phi is false and psi is true, then phi disjunction psi remains true. The only time that phi disjunction psi is false is when both phi and psi are false. Our conditional statement is true in 3 instances as well. It's true when, it's true when phi is true and psi is true. So if A, then B. If A is true and B is true, that holds. So we get a true. If phi is false, in either case we get true, right? So if I tell my son, if you eat all your dinner, then you'll get dessert. If he doesn't eat his dinner, then that statement remains true. It doesn't prove that statement to be false, because if I give him dessert or I don't give him dessert, it's still true in both instances. Okay. The instance where he doesn't eat his dinner and I still give him dessert can often strike students as weird. But just think of it this way. It doesn't provide a counterexample to what I said. You know, if I'd said you get dessert if and only if you eat your dinner, then if he hadn't eaten it, it would make sense. If he hadn't eaten it and he got dessert, my statement would have been false. But in this instance, I didn't say that that's the only way he's going to get dessert. I just said that if he does do that, then it will follow. Okay. The only time phi conditional psi is false is when the antecedent is met, but the conditional doesn't follow, right? So if I said, Max, if you eat your dinner, you're going to get dessert, and then he ate his dinner and I just cold-heartedly didn't give him dessert, I would have lied to him previously, right? And that seems to make sense to us, I think. So the only time the conditional statement goes false is when the antecedent is true and the conditional is false. In all other instances, the conditional is true. And we can talk more about this if you guys would like in our discussion sections. The reason that we tend to push back against this is because of sort of pragmatic considerations. So again, natural languages are set up so that people tend to say things that are as informative as possible. So it'd be weird to say this line of it and still give the person the thing afterwards. But that's merely a pragmatic feature of natural language. There are tests for investigating the implications of our utterances, and that is revealed to be an implication by means of those tests, but not part of the semantic content or the underlying content of the sentence itself, which is really what we're focused on in logic. So just remember this rule for conditional. If it seems unnatural to you, still ingrain it in your brain and use it. We'll see later on how it makes sense. And then finally, we have our biconditional connective. So we have here phi and psi. If both of these are true, then phi if and only if psi is true. And if both of them are false, then phi if and only if psi is true. But if their truth value comes apart, then phi if and only if psi isn't true, right? If we're saying, again, Max, you get dessert if and only if you eat your dinner, Then if he eats his dinner but doesn't get dessert, I've lied to him. And if he doesn't eat his dinner but does get dessert, then I've lied to him as well. Okay, so how are we going to translate sentences using our connectives? Let's just revisit this for a moment. Well, we know that some complex sentences contain only one connective. So consider this sentence: Petra has had dinner if she went to the Commons. Well, first of all, what we want to do to translate this is to replace the atomic sentences with sentence letters, being sure to include a key. So here I've done that. So we have A standing for Petra went to the Commons, and B standing for Petra has had dinner. And if we plug those into the sentence, then we just get the following: B if A, right? So that is our complex sentence so far. And then what we want to do is replace the natural language logical connectives with the relevant SL connective. And this may require us to rearrange the atomic sentences. So again, we know that if is going to put us in mind of a conditional, and if is going to identify the antecedent of the conditional. So that's the thing that appears before the horseshoe. So what we'd end up translating this as is if A, then B, right? And so this is what our sentence has come down to. Petra has had dinner if she went to the Commons becomes if A, then B, where A stands for Petra went to the Commons and B stands for Petra has had dinner. And this captures the logical form of the normal, of the English language sentence. So we can appreciate the logical properties of this sentence then using the relevant connectives characteristic truth tables, right? So we can just appreciate the logical properties of this by thinking about the truth table for if A, then B. And so here we get that. So we know that this sentence is true. If Petra went to the Commons and she had dinner, that means that if Petra went to the Commons and she has had dinner is true, or Petra has had dinner if she went to the Commons, the way the sentence was in ordinary English. And we also know it's true if Petra has not gone to the Commons, whether or not she had dinner, right? So we just said, if she's gone to the Commons and she's had dinner, there might be some other way in which she's had dinner. So the sentence isn't proved false by her having had dinner when she didn't go to the Commons, nor is it proved false by her not having had dinner when she didn't go to the Commons. The only time this sentence is false is if Petra went to the Commons and she didn't have dinner there. If I told you Petra's had dinner if she went to the Commons, and then you find out that she went to the Commons and didn't have dinner, then you know that I've spoken falsely in that case. So each row again in this truth table corresponds to an interpretation. So this is very important to note. So each row here stands for a interpretation, and that is just a possible way of assigning truth values to atomic sentences. So this sentence again is Petra went to the Commons. B is Petra has had dinner. And it's possible for each of these atomic sentences for them to be either true or false. But those are the only truth values in classical logic. It can be true or it can be false. So we have here instances where this sentence, A, Petra went to the Commons, is true, and instances where it's false. And we have instances in which Petra has had dinner are true and false. And this captures all the way that those sentences may be true or false relative to one another. So the truth table tells us what the truth value of the complex sentence will be for each interpretation, right? So a possible way the world might be is Petra's having gone to the Commons and Petra's having had dinner. And in that case, if A, then B will be true. But there are other possible ways the world may be too. It could be true that Petra went to the Commons, but false that Petra has had dinner. It could be false that Petra went to the Commons, but true that she had dinner. And both of these could be false. So setting up the truth table in this way captures all of the ways the world might be relative to these two sentences' truth values, right? They can both be true. One can be true and the other can be false, both ways, or they can both be false. And so when we set up our truth table, we want to be mindful of trying to capture all of the ways in which the atomic sentences may be true or false relative to one another. All right, so let's look at sentences with multiple connectives. So we've looked at simple complex sentences, sentences that have only one connective, but some complex sentences are more complex. So consider this one. Alex went to the movies, or he didn't. And if he didn't, then I'm a monkey's uncle. So this sentence is more complex in each of two ways. It involves more connectives, and it also involves more atomic sentences. So again, we'll want to replace atomic sentences with sentence letters. So how many atomic sentences make up this sentence? Sorry, I misspoke. It only involves two. So the two sentences, the atomic sentences involved here are Alex went to the movies, A, and B, I am a monkey's uncle. But this sentence is made more complex because of the use of negation. So here is an initial translation of this sentence, replacing the atomic sentences with their sentence letters. So we get A or A not, and if A not, then B. Okay. And then what we want to do again is replace the natural language logical connectives with the relevant SL connectives. And we would reorder as needed here. So we would have A or not A and not A. If not A, then B. But look, this is confusing. We don't know what goes with what. We don't know if the and is connecting this whole disjunctive statement or if it's just saying a relationship between these two parts. So we need to add parentheses to identify the sub-sentences that make up this complex sentence. And so this sentence would look like this. So we have both A or not A, and if not A, then B. And so this is a well-formed formula that is perfectly clear in its truth value in identifying the underlying logical structure of this sentence. So truth tables for sentences with multiple connectives look more interesting than the simple connectives we've looked at so far. And this week you'll be practicing the skill of constructing these truth tables for more complex sentences. And again, this will allow us to assess when these sentences are true or when they're false. So if a sentence has only one connective, we can assess its logical properties by plugging it into the characteristic truth table for that connective, like we did with the sentence involving Petra a few slides ago. But we'll have to do a little more work to construct a truth table for a sentence constructed from multiple connectives. Fortunately, though, the truth table method provides a purely mechanical procedure for evaluating infinitely complex sentences built out of atomic sentences conjoined by any number of logical connectives. And so we'll now introduce this procedure. Okay, so recall our previous sentence. It said both A or not A, and it's not the case that A, if it's not the case that A, then B. So a complete truth table for this sentence will contain one row for each possible combination of true and false for all of the sentence letters the sentence contains. So there are two sentence letters here. So the number of rows that we need is 2 to the power of n, where n is the number of sentence letters. And since there are only two atomic sentences here, two sentence letters, then we get 4 rows, okay? Now, on the left side of this table, we're going to set up reference columns for our atomic sentences. And so that'll look like this. So we have A and B. Those are the two atomic sentences that go into composing this complex sentence. And again, we want to set up situations that capture every possible way these sentences might be true or false relative to each other. So we're going to use the following procedure to ensure that each row of our table captures a unique possible combination of truth values for the atomic sentences that make up our complex sentence. What we're going to do is we're going to start with the reference column furthest to the left, and we're going to fill in the first half of the rows with 1s and the second half with 0s. So that'll look like this. So our truth table, we've got 1, 1, 0, 0. Now what we're going to do is we're going to move to the next column to the right. So that's a column for B. And we're going to fill in the first and third quarter of rows with 1s and the second and fourth quarter with zeros. So that'll look like this. Because there are only 4 rows in this table, the first quarter is 1 row. But if we had more logical connectives here, like if we had A, B, C, and we'll be seeing sentences that have 3 or 4 atomic sentences that make them up, then we would start by dividing the first one in half, and it might be, you know, if we have 3 sentences making it up, then it would be the first 4 rows that would be true, and the next 4 rows that would be false. We would move on to B then and have the first 2 rows being true, the second 2 rows being false, the next 2 rows being true, and the last 2 rows being false. And then if we moved on to C, it would look more like B does here, so it would be true, false, true, false, true, false. So I hope that makes sense. So we're setting up these reference columns in this way. So we have here, so again, yeah, as I was just saying, you would keep proceeding in this way until you end with alternating 1s and 0s in the rightmost reference column. So here, because this has 2 atomic sentences that compose it, we've exhausted the possible ways that the atomic sentences might be true or false relative to one another. Okay, now I've spaced out our sentence a little bit more to make it so that we can represent the truth values of our complex sentences that are going into composing our whole entire sentence here a little bit more clearly, right? So we know, so we're now going to determine the order in which we'll assign truth values. So the way to do that is to start by looking at the atomic sentences. And then you need to ask yourself, does any connective apply to an atomic sentence directly? And so what you want to do is circle that connective. And a hint here is that if it's applying to just one atomic sentence, the connective will always be negation. So we want to look at negation, and we see here that there are 2 sentences where a connective applies only to an atomic sentence, not A in the first conjunct here, and not A in the second conjunct. And so we can ask ourselves then, is that connective that you just circled used as a sentence input for another connective? If not, then that connective you just circled is the main connective. If it is, look for the connective that applies directly to the sentence you just circled and circle that next connective. So this is the next connective, right? So we have not A here, and then or is applied to that thing on the left-hand conjunct, and on the right-hand conjunct, it is a conditional that not A goes into. And so you continue this process until you have no more connectives to circle. And the connective you circled last is the main connective, okay? And so now the way that you're going to solve this or construct this truth table is you want to work outwards. You want to start with the connectives you circled first and assign truth values to the main connective last. So this is very important. So we start here with the negated A's, right? And then we're going to move out to these smaller chunks. So the disjunctive sentence on the left-hand side of the conjunct and the conditional sentence on the right-hand side of the conjunct. And then ultimately we'll plug in the truth values for our conjunction. Okay, so first, not A's. Second, the or and the if then, the disjunction and the conditional. And then ultimately the conjunction is how we're going to work this truth table. And so now we can fill in truth values for each connective in the table in the order we established previously, just using the characteristic truth table for our connective. So the only thing you should need to refer to here is the reference columns and the rule for the relevant connective you're filling in. So again, if we have not A, negation would tell us if we have a true underlying sentence A, then not A becomes false. And if we have a false underlying sentence A, then not A becomes true. So we get these values. Same over here. Okay, so that would be the first row we would fill in our truth table. Now we want to move out to deal with the second connectives, the second level of connectives we want to look at. So that's this disjunction and this conditional. And so we can look here for reference column A. So A, if A is true, and not A is false, then A disjunction A will be true. If A is true and not A is false, then A disjunction A will be true. And in each of these instances, not A is true. So even though A is false, these also are going to be true. So the truth value for the disjunction on the left-hand side is as follows. I'm sorry, here I have translated the truth value from the atomic sentences into our truth table itself, just to make it so we don't have to look back at the reference table. But what I was just saying remains true, so we get true, 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 true here. And now on this side, we know that a conditional statement is false only if the antecedent is true and the conditional is false. So this one will only be false in this last row. Okay, and now we're going to do our main connective, and we know that our sentence, a conjunctive sentence, is true if and only if both of the conjuncts are true. So this sentence will be true in the first 3 rows and false in the last. And this is the underlying value of this complex sentence we looked at, right? Which again was either Bob went to the movies or Bob didn't go to the movies, and if he didn't go to the movies, then I'm a monkey's uncle. So that sentence is true in a situation where Bob went to the movies and I'm a monkey's uncle, where Bob went to the movies and I'm not a monkey's uncle, where Bob didn't go to the movies and I'm a monkey's uncle, but it's false if Bob didn't go to the movies and I am not a monkey's uncle. Okay? So we've recovered the truth value for this complex sentence simply by knowing the underlying truth values of the atomic sentences and how our logical connectives work. And that's because our logical connectives are truth functional. This, again, is the row that identifies the truth value of this complex sentence. And the truth table for this sentence involving multiple connectives reveals that the sentence is Alex, not Bob. The complex sentence, Alex went to the movies or he didn't, and if he didn't, then I'm a monkey's uncle, is true in any situation except one, and that's where Alex did not go to the movies and I am not a monkey's uncle. That is any situation except the one captured by row 4. So again, this tool allowed us to tell under what situations this complex sentence would be true based simply on our knowledge of the connectives and the underlying truth value of the atomic sentences. And that's because our logical connectives are truth functional. That's why we don't have to know any other information than those things. That is all for Unit 6. And I'll be posting Unit 7 later today for you all to have a look at. There's only 2 units this week. And you'll have a quiz after that, a short quiz to take, and we'll be practicing truth tables for the rest of this week. Have a nice day.